Something is living inside your device right now that you never installed, never approved, and cannot see under normal circumstances. It is not a virus. It is not spyware. It is something far more calculated than that, something engineered directly into the core of your operating system by the same companies that charged you hundreds, sometimes thousands of dollars for that device. You have been buying extra storage. You have been deleting files you actually wanted to keep. You have been blaming yourself for running out of space. But the truth is brutally simple. Your device was designed to fill up. And today, that design gets exposed. Nobody talks about the moment it first happens. You're going about your day, trying to save a file or capture a video of something that matters to you, and your device puts up a wall. Storage full. And you stand there genuinely baffled because you have been careful. You have managed your files. You watched your storage indicator. You did everything right. Yet the device is telling you that the space is gone, and it offers you zero explanation for where it went. That confusion is not accidental. That confusion is a product decision. And once you understand what is actually happening inside your device at a file system level, you will realize that the storage crisis you have been experiencing is not the result of poor personal management. It is the result of deliberate architectural choices that prioritize system behavior over user transparency. The technology industry has built an extraordinary business model around storage anxiety. Cloud storage, subscriptions, expanded device tiers at higher price points, external hard drives, memory cards, USB sticks. The entire ecosystem of storage expansion products generates billions of dollars in annual revenue. And a significant portion of that revenue comes from users who do not actually need more storage. They need access to the storage they already have. They need visibility into the portions of their device that have been silently claimed by the operating system, by applications, and by background processes, running in ways that are never surfaced to the user. The storage is there. It has been there all along. It is just sitting behind walls that require specific knowledge to identify and dismantle. This is that knowledge. Start with something that Windows users have almost certainly never opened or examined, the page file. On every Windows machine running Windows 10 or Windows 11, there's a hidden system file sitting at the very root of the C drive called pagefile.sys. This file is the physical manifestation of Windows virtual memory. When your computer's physical RAM begins to fill up during intensive tasks, Windows starts using a portion of your hard drive, or SSD, as an overflow zone, essentially pretending it is RAM and pushing a data back and forth between real memory and this page file. The technical term for this process is paging, and the file that enables it is pagefile.sys. The size of this file is dynamic by default, meaning Windows adjusts it automatically based on system demand. On a machine with 8 gigabytes of physical RAM, pagefile.sys might typically sit at around 8 to 12 gigabytes. On a system with 16 gigabytes of RAM, it can expand to 16 gigabytes or beyond during heavy usage. On a system with 32 gigabytes of RAM, which is increasingly common on modern creative workstations, the page file can theoretically grow to match or exceed that figure under extreme memory pressure. This is a file that most users have no idea exists, consuming storage equivalent to their entire RAM capacity, located in a place that is hidden by default from Windows Explorer, and never mentioned during device setup or in any standard user guide. Now, the page file is something you want to leave enabled on most systems. Disabling it entirely can cause stability problems, particularly if you run memory-intensive applications. But what you can do, and what most users never realize they have control over, is set a fixed maximum size for the page file rather than letting Windows manage it dynamically. By navigating to System Properties, then Advanced, then Performance Settings, then the Advanced tab, and finally clicking Change under Virtual Memory, you can manually configure page file size. Setting a fixed size appropriate to your usage patterns prevents Windows from expanding it opportunistically during intensive sessions and then failing to fully release that space afterward. You can also move the page file to a secondary drive if you have one, freeing up that space on your primary system drive entirely. These are controls that exist within Windows. They are accessible to any user. They are simply never surfaced in any visible or intuitive way. Now, consider what happens every time Microsoft releases a major Windows update. Not the small monthly security patches, the big cumulative feature updates that roll out twice a year and that change significant aspects of how the operating system functions. When one of these updates installs, Windows performs a preparation process that most users are only dimly aware of, and that preparation process involves maintaining a complete archive of system files in a location called the Component Store. On your drive, this appears as the WinExXS folder inside the Windows System Directory. What makes this folder uniquely frustrating is the way Windows reports its size. If you right-click the WinExXS folder and check its properties, Windows will report a size that seems alarming, often 15, 20, or even 30 gigabytes on a well-used system. But Microsoft will also tell you, if you look at their official documentation, that this reported size is misleading because it includes hard links to files that are actually stored elsewhere, meaning the folder looks larger than the space it actually occupies independently. This is technically accurate. However, it is also conveniently used to dismiss legitimate concerns about the folder's real storage impact. The truth, according to independent storage analysis conducted using tools like Winderstat and TreeSize, is that even accounting for hard link inflation, WinSCHS on age systems does genuinely consume between 8 and 15 gigabytes of unique storage in many cases. The version management inside this folder, old copies of system components kept around for backward compatibility with legacy software, represents years of update history stacked on top of each other with no automatic pruning. Running the command line tool DISM with the start component cleanup flag, or using the disk cleanup utility in system files mode, will prompt Windows to analyze this store and remove component versions that have been superseded by newer updates. This is a sanctioned, safe operation that Microsoft documents and that can realistically recover 4 to 12 gigabytes of genuine storage on a system that has been through multiple update generations. There's another Windows folder that deserves far more attention than it receives, the Prefetch folder, located at C Windows Prefetch. Windows uses a performance optimization system called Superfetch, and later ReadyBoost and ReadyBoot, to monitor which applications you launch frequently and preload portions of those applications into memory at startup, so they open faster when you call for them. The Prefetch folder stores the data that enables this optimization, small files that map application launch sequences and resource requirements. Individually, these files are modest in size, but over years of use, the Prefetch folder can accumulate hundreds of files representing applications you installed and later removed, programs you ran once and deleted, and old versions of software that has since been updated. Windows is supposed to manage the Prefetch folder automatically, limiting it to a maximum of 128 files, and purging the oldest entries when that limit is reached. In practice, on systems that have been through multiple Windows upgrades without a clean installation, the automatic management does not always function cleanly. Beyond the file count issue, there is also the broader question of how the Superfetch service itself manages prefetch data. On systems with SSDs, where the performance benefit of prefetching is minimal because SSDs already access data nearly instantaneously, Superfetch can sometimes be configured more conservatively without any perceptible impact on application launch times. Moving over to the Mac ecosystem now, and entering territory that Apple has worked very hard to make invisible. Open any MacBook that has been in daily use for 18 months or more and navigate to the System Information Storage panel, the one accessible from the Apple menu through About This Mac, and then More Info, and then Storage. You will see a visual breakdown of your storage consumption organized into categories: apps, documents, photos, messages, iOS files, and then, at the far end of the bar, usually rendered in a neutral gray or muted tone, a category labeled System Data. On many Mac systems, this single category, System Data, is the second or third largest consumer of storage on the entire drive, behind only user documents and applications. And when users try to find out what system data actually contains, they run directly into a wall. Apple's official documentation describes system data as encompassing files that cannot be categorized elsewhere. That is not a description, that is a deflection. What lives inside system data includes local time machine snapshots, cached content from system processes, virtual memory swap files, sleep image files, diagnostic logs, security databases, font caches, and various other system-level storage that Apple has deliberately grouped into a single impenetrable category to prevent users from directly managing it. The sleep image file is worth examining specifically because it is a Mac analog to the Windows hibernation file and receives almost no coverage in mainstream technology content. When a Mac with a non-flash storage model, your certain MacBook configurations, enters a deep sleep state called safe sleep, macOS writes the entire contents of RAM to a file on your internal drive, so that the system can recover your session even if battery power is completely exhausted during sleep. This file lives at private Strasbourg VM sleep image and is precisely the size of your installed RAM. A MacBook with 16 gigabytes of RAM has a 16 gigabyte sleep image file sitting permanently on its internal drive. A machine with 32 gigabytes of RAM carries a 32 gigabyte sleep image file. On modern MacBooks with Apple Silicon processors, the behavior of this file has changed somewhat because the architecture handles power states differently. But on Intel-based MacBooks running macOS Ventura, Sonoma, or Sequoia, this file remains a significant storage consumer that most users are entirely unaware of. You can check whether your Mac is maintaining this file by navigating to that path through Terminal. If you use your MacBook primarily in locations where power is readily available and the battery dead during sleep scenario is not a real concern for you, there are ways to configure sleep behavior to reduce reliance on this file, though any such configuration changes should be approached carefully and with an understanding of the trade-offs involved. Within the Tust-Trak-Traktor library directory, which sits inside your home folder and remains invisible in Finder unless you actively reveal hidden files, there is a subfolder called Application Support that deserves specific examination, apart from the cache discussion. Application support is where applications store persistent data that is not cache, things like local databases, downloaded content, configuration files, and application-specific user data. The distinction from cache is that these files are not meant to be ephemeral. They are meant to persist. The problem is that when you uninstall an application on Mac by simply dragging it to the trash, the application binary disappears, but the contents of its application support folder do not. Every application you have ever installed on your Mac, then later deleted, has potentially left a folder full of persistent data inside Amorunchdorf's library application support that continues to occupy your storage indefinitely after the application itself is gone. A music production application might leave behind gigabytes of sample libraries and project data. A video application might leave behind render presets and project caches. A development tool might leave behind package caches, compiled dependencies, and workspace configuration data. None of this is cleaned up automatically when you move the application to the trash, because macOS treats the application and its support data as separate entities from a storage management perspective. Tools like App Cleaner, which is a free third-party utility, specifically address this gap by identifying and offering to remove associated data when you uninstall an application. But Apple's own first-party uninstall mechanism, dragging to trash, does not perform this cleanup, and the majority of users never realize they need to do it manually. The iPhone storage conversation has a specific dimension in 2024 and 2025 that deserves direct attention, which is the behavior of the iOS Messages application and the storage it accumulates over time. Text messages, iMessages, shared photos, videos, voice memos, GIFs, links, and all the other content types that modern messaging includes are stored locally on your device inside the Messages application's data container. On a device that has been in daily use for 2 or 3 years with active message threads, group chats, media-heavy conversations, long-running threads with friends and family, the Messages application can accumulate 3, 5, or even 8 gigabytes of storage. Much of this is media content that was shared with you in conversations and that you viewed once, found entertaining or useful in the moment, and then completely forgot about. It continues to sit on your device indefinitely unless you manually configure Messages to automatically delete message history after a set period. You can find this setting inside the Settings application, under Messages, under Message History, where you can set messages to expire after 30 days or 1 year rather than keeping them forever. For most users, this single configuration change, combined with a manual review of individual conversations to delete those with high media content, can recover several gigabytes of storage immediately and prevent continuous accumulation going forward. Android users face a hidden storage challenge that has intensified with recent changes to how Google manages file system access on Android 11 and all subsequent versions through Android 14 and 15. In older versions of Android, users could freely browse their device's internal storage using any file manager application and access virtually any folder, including the application data directories. Starting with Android 11, Google implemented what they called scoped storage, a security-focused storage access model that restricts applications from reading and writing to arbitrary storage locations and requires them to operate within defined sandboxes. This was a genuine security improvement, but it had an unintended practical consequence. It made large portions of device storage effectively invisible and inaccessible to users through conventional means. The Android data folder, which houses application-specific data files for every application installed on the device, is now inaccessible through most file manager applications without special permissions that Google does not grant to third-party apps on modern Android versions. Yet this folder continues to accumulate data from every application running on the device. Navigation applications, downloading offline maps, social platforms caching video content, gaming applications, storing downloaded asset packs, productivity tools, saving local copies of cloud documents. All of this flows into Android data, and the user's ability to directly manage or even clearly see what is accumulating there has been substantially curtailed. Connecting the device to a computer via USB in file transfer mode and accessing the folder through the computer's file manager remains one of the few pathways that allows users to examine and clean this directory. And even then, the access is read-only on the most recent Android versions for certain protected directories. There's a category of hidden storage that cuts across all platforms and that has grown dramatically in relevance over the past 3 years, as the applications we use daily have become increasingly complex web-connected services rather than simple local tools. It is the storage consumed by application update mechanisms. Almost every modern application, whether on Windows, Mac, Android, or iOS, uses some form of staged update delivery, where new application versions are downloaded in the background before they are installed. On desktop platforms, this means update packages are downloaded to temporary staging directories and held there until the application is ready to install them, which might not happen immediately if the application is actively in use. On mobile platforms, this means downloaded update packages sitting in system-managed storage, waiting for a convenient installation moment, such as when the device is plugged in and idle. In both cases, there are scenarios where update packages are downloaded, held in staging, and then superseded by a newer update before they are ever installed, leaving behind a downloaded package for a version of the application that will never be installed, occupying storage until a cleanup routine runs and catches it. Multiply this across dozens of installed applications, updating on independent schedules, and you have a continuous background process of download staging that collectively consumes storage in ways that are almost impossible for users to observe or quantify from the outside. Browser storage has undergone a fundamental transformation in the era of progressive web applications and service workers, and the storage implications of that transformation are not well understood by most users. When you visit a website that is designed as a progressive web application, and in 2025, this category includes many commonly used tools like productivity applications, social platforms, and media services. Your browser downloads and locally installs a version of that application. Service workers, which are JavaScript processes that run in the background independent of any open browser tab, manage this local installation and keep it updated. They also cache application resources, intercept network requests, enable offline functionality, and store application data locally using browser APIs like IndexedDB and the Cache Storage API. All of this local storage accumulates in your browser's profile directory on your device. A browser that has been used actively to access progressive web applications over a period of a year or more can maintain several gigabytes of service worker caches and IndexedDB databases for applications you may have visited only a handful of times. Unlike traditional browser cache, which most users know to clear periodically, service worker caches and application databases are rarely touched during a standard cache clearing operation. They require specifically navigating to the browser's developer tools, opening the application panel, and manually clearing storage for individual origins, a process that is accessible only to users who know the browser's developer tools interface and understand what they are looking at. What makes the hidden storage problem particularly acute in the current technological environment of 2025 is the convergence of several simultaneous pressures that have not been this intense at any previous point in consumer technology history. Artificial intelligence features are being embedded directly into operating systems and applications, and those features require local model files and inference data to be stored on the device. Windows 11, Copilot Plus features, Apple Intelligence on Mac and iOS devices, and on-device AI in Android applications all require local storage for model weights and associated data that did not exist as storage consumers 2 years ago. The AI features in Windows 11's latest releases, for instance, require significant local storage for the neural processing models that power features like Recall, which continuously captures screenshots of everything you do on your computer and stores them in a searchable local database. The storage implications of AI features operating at the operating system level represent a new category of hidden storage consumption that has no historical precedent in consumer computing, and that is expanding rapidly with every new software release from every major platform. Here is the actionable reality of everything that has been laid out here. The storage on your device is not as depleted as it appears. It has been claimed by systems that were designed to operate below the surface of your awareness, by mechanisms that have been there since you first powered on the device, and by behaviors that the companies behind them have never had a strong incentive to make transparent to you. The path to reclaiming it requires navigating to places you were not meant to find, running commands you were not told existed, and making configuration changes that were never explained during device setup. On Windows, the tools are the DIASM command line utility, the disk cleanup administrator mode, the virtual memory configuration panel, and the service management console for temporarily halting background services during cleanup. On Mac, the tools are the terminal application, the Temuto command set for snapshot management, and third-party utilities like App Cleaner for orphaned application data. On iPhone, the path runs through Settings, then General, then iPhone Storage, where you can review per application storage usage and enable automatic cleanup features. On Android, the combination of developer mode, USB debugging, and desktop file manager access provides the deepest available window into the file system as it actually exists. The storage you recover using this knowledge is not new storage. It is not storage you are creating through some technical magic. It is storage that was always yours. Storage you purchased. Storage your device has been holding hostage inside folders designed to be invisible, maintained by systems designed to operate without your input or awareness, serving purposes that range from genuinely useful to completely indefensible, depending on the specific folder and how long it has been left unmanaged. Every gigabyte you clear is a gigabyte that stops requiring you to manage your actual files with artificial scarcity. Every folder you eliminate is a folder that was taking up space without your consent for an unknown period of time. The question that lingers after all of this, the question that should genuinely unsettle you, is not about the folders themselves. It is about what comes next. As devices become more capable, as operating systems grow more complex, as artificial intelligence becomes embedded in every layer of the software stack, how much of your storage will be consumed by processes and files you have no visibility into, no control over, and no easy mechanism to address? The companies building these systems are moving faster than the communities explaining them, and the gap between what your device is actually doing with your storage and what it is telling you it is doing with your storage has never been wider than it is right now. Which means the most important question is not what you delete today. It is what they will hide from you tomorrow.